Now we want to go over how we can calculate the cross product in maybe a more smooth manner, something that doesn't require just such like a rigorous or lengthy definition and formula, and where it's just kind of mindless plugging in and quote unquote plug and chug, right? And so one method of computing the cross product that is quite handy is using determinants. So first, let's talk about what determinants are and how we calculate them. So first, let's consider the case, a 2 by 2 case. So we're going to look at the case when our matrix, so we're going to have a matrix M, we can just call it like matrix A, B, C, D, right? Where for us, A, B, C, and D are all real numbers here. And a matrix is a way of encoding information. It's very useful in linear algebra and matrix theory if you've taken matrix theory already, or if you haven't. The context that we're going to be looking in the context that we're going to be using matrices is to as like a series of row vectors. So kind of juxtaposing row vectors can give you a matrix. But anyway, what we want to look about now is calculating the determinant of a 2 by 2 matrix. And the determinant is an operation that you do, and it spits out a number. So the determinant of a 2 by 2 matrix is as follows. It's denoted by square, or not square, but vertical brackets here versus like enlarged parentheses for the matrix itself. When we're actually taking the determinant, we indicate it with vertical brackets or vertical lines. And the determinant of a 2 by 2 matrix is defined as you take product along the diagonal of this matrix. And so we get AD, and then you subtract the anti-diagonal, which is BC. So the determinant of a 2 by 2 matrix is AD minus BC. So a very quick example is, let's calculate the determinant of the matrix 3, -2, 5, 1. It's AD, so 3 times 1 minus BC, so -2, 5, which gives us 3 plus 15. That's not how you multiply. That would be 3 plus 10, which is 13. And so the determinant of this matrix is 13. Now for a 3 by 3 matrix, let's look at 3 by 3 determinants. The determinant for a 3 by 3 matrix is calculated in terms of 2 by 2 matrices. So, or in terms of determinants of 2 by 2 submatrices. And so we need to keep this formula in mind as we calculate the determinant for a 3 by 3 matrix. So let's say we have the matrix A, B, C, D, E, F, G, H, I. Let's kind of go down the alphabet here. A 3 by 3 determinant is calculated as follows. So I'll give a formula. First, I'll just write the formula and then give some intuition behind it. So it's A times the 2 by 2 determinant of the submatrix EFHI minus B times the 2 by 2 determinant of the submatrix DFGI, and then plus C times the 2 by 2 determinant of DEGH. And so this is a formula for calculating a 3 by 3 determinant, or a determinant of a 3 by 3 matrix. And now let's give some intuition on how we can remember this formula. The first term here, I'll indicate in red. you see we take A, and we take A times the submatrix that is kind of catty corner, if you will, from A. And here's how you think about this. To find the 2x2 submatrix, you find the 2x2 submatrix by removing the row and column that A belongs to. Okay. And so if you will, here I'll draw another copy of our matrix down here so I can have a little more room to make marks. You take A, right? And then we take the row and column that contains A, and you forget about them, right? And so we took A, and then we forgot about the row and columns that A belongs to. And you see what's left. We have a 2x2 matrix that's left. And that's exactly this 2x2 matrix, EFHI. And then we take its determinant. And so now, what about B? And so you alternate signs always here. Notice the signs of each term goes plus, minus, plus. Next, maybe I'll use green here. It's minus because we alternate the sign. And then B times the submatrix DG and FI. And so you can see this is exactly the matrix like DFGI here. And what did we do this time? Well, we did the same thing, but now we deleted the row and column that B belongs to. So let me copy our matrix again here, and we can see where we got the submatrix from. Okay, we have A, B, C, D, E, F, G, H, I. And this time, we took B, and now we want to forget about the row and column that B belongs to. And you can see, what is the resulting 2x2 matrix? Well, it's exactly this submatrix we have up here. It's DFGI. And so let's do this one last time, and hopefully by now you can start to see a pattern of what we've got. We take our matrix A, B, C, D, E, F, G, H, I. Now, let's take C here, delete the row and column that C belongs to, and look at the corresponding matrix that's left. And you'll see it's exactly this DEGH. And so over here, we took C times the determinant of the submatrix DEGH. And this is our formula for being able to calculate a determinant of a 3x3 matrix. So this is the formula, and hopefully now with this intuition, it becomes, after some examples, more or less routine. You can just kind of look at the numbers and say, okay, A times this determinant minus B times this determinant plus C times this determinant. Okay, and so let's do an example here. So we can start to get comfortable with doing this, right? Let's find the determinant of the matrix 2, 5, -1, -1, 1, 3, -2, 3, 4, okay? And so what do we do first? Well, we take the first entry in the top row, and then we multiply it by the determinant of what's left when you delete the row and column that 2 belongs to, right? So this is 2 times the determinant of 1, 3, 3, 4. And then you alternate the sign. So it was plus in the first term, so now it's minus. And then we take 5 times the determinant of what's left when you delete the row and column that 5 belongs to. So this looks like we're going to have minus 5 times the determinant of negative 1, 3, 2, 4. And then plus, we're going to have negative 1. And then you can see by the same argument here, in green, we get times the determinant of negative 1, 1, 2, 3. And so simplifying this, we remember how to take a 2 by 2 determinant. That's 2 times 4 minus 9 minus 5 times negative 4 minus 6 minus, because of the negative 1 there, and then it's going to be negative 3 minus 2. Simplifying, we're going to get, so 2 times negative 5 is negative 10. And then it looks like we have negative 4. So this should be, let's see, we have negative 4. Excuse me, I see my mistake. This was a negative 2, right? So this is negative. So this is plus 6 here. I miscopied the negative. And so we have negative 4 plus 6, which is 2. So then we have minus 10 again, and then 6. And if this was a negative 2, then this will be plus again, right? And so we have negative 3 plus 2, which is negative 1, but then it's minus a negative 1, so plus 1. And so our answer is negative 19. Right? And so here's how we can calculate a determinant of a 3 by 3 matrix, just following this formula here. Okay. And so why is this so useful? Why am I teaching determinants? And the following theorem will give some insight as to why becoming very good at calculating 3 by 3 determinants will make you very good at taking cross products of two vectors. So let's let U be U1, U2, U3, and let's let V be the vector V1, V2, V3. If we consider the matrix of row vectors, row vector just means like each row of the matrix is a vector, right? So let's call it M. If we consider the following matrix of row vectors, and the first vector is just going to be I hat, J hat, K hat. The second vector is going to be U, so U1, U2, U3. And the third vector is going to be V1, V2, V3. So if we consider this matrix M, which is comprised of 3 row vectors, right? The vector 1, 1, 1, the vector U, and then the vector V. If we look at this matrix, then U cross V is the determinant of M. So U cross V is the determinant of I hat, J hat, K hat, U1, U2, U3, V1, V2, V3. And if we compute this, what do we get? We get, let's take the determinant, right? We're going to get, so first we start with I hat, and then it's going to be I hat times the determinant of the bottom right 2 by 2. And so that's U2, U3, V2, V3 times I hat, and then minus, and that's our formula for the determinant. Then we go to J hat. And we take the corresponding 2 by 2, right? And so this is going to be then times the determinant of U1, U3, V1, V3, J hat, and then plus, sorry, I have to write it down here, the term involving K hat, which looks like it's going to be the determinant of U1, U2, V1, V2, K hat. And if you expand this one step farther, then you see that this is exactly the formula for the cross product that we had previously in terms of like u sub i's and v sub i's. And now we don't have to memorize it. Now we just have to take 3x3 determinants. Because if we take a 3x3 determinant, what are we going to get? Well, this would equal, right? The 2x2 determinant here is u2v3 minus u3v2. And so you get like u2v3 minus u3v2 I hat. And then, oops, wrong way. And then it'd be minus u1v3 u3v1, right? So minus u1v3 minus u3v1 j hat, and then plus, take the 2x2 determinant of the submatrix in front of K would be u1v2 minus u2v1. So u1v2 minus u2v1 K hat. And this is exactly the formula for cross product that we derived in the previous video. And so now, given two vectors u and v, we'll just immediately go to this setup here. We'll just say, okay, well, u cross v is the 3x3 determinant given by, or the determinant given by the 3x3 matrix once we plug our vectors in. And so let's do an example. So we can see that this is a lot better and a lot more smooth than just simply trying to each time label our numbers like u1 through u3 and v1 through v3 and then trying to plug them in, et cetera, et cetera. Now, so if we have a equals the vector 5, 2, -1, and b equals the vector 0, -1, 4, let's compute a cross b. Okay, well, a cross b, now we just go straight to the setup. Is I hat, j hat, k hat. And then in the second row, we have the vector a, so 5, 2, -1. And then in the second, or in the third row, we have the second vector, which is 0, -1, 4, right? And now let's compute the cross product by computing a determinant, right? And so this is going to be the determinant of this 2x2 matrix. So we have 2, -1, -1, 4. Whoops. Let's put that on the inside of the brackets. 2, -1, -1, 4 I hat minus 5, -1, 0, 4 j hat plus 5, 2, 0, -1 k hat. Right? Because, again, you can go through this as slowly as you need each time until you can just kind of by inspection see what the submatrices are going to be, right? So for I, we delete the row and column that I belongs to, and then we look at the corresponding submatrix, and we saw that was this one. We do the same thing for J hat here. We delete the row and column that J belongs to, and then we find the corresponding submatrix, which we did here. Remember, the second term is always a negative. And then we do the same thing for K hat, right? We take K hat, delete the row and column that K belongs to, and look at what's left. And what's left is 5, 2, 0, -1. And this is what we did here. And now we can fully compute what the cross product should be here, right? By now taking 2x2 determinants. So the 2x2 determinant in front of I hat, it looks like it's going to be 2 times 4, so it's 8, and then minus -1 times -1. So there's 3 negatives in there, right? It's minus -1 times -1, which 3 minuses means minus, right? And so this is 8 minus 1. I hat, and then minus, looks like we'll have 20. We'll have 20 minus 0, so minus 20 j hat. And then for k hat, it looks like we'll have negative 5 minus 0, so negative 5 k hat. And so our cross product, A cross B, is then the vector 7, negative 20, negative 5, like this. And so this is how we compute our cross product now. And you can see it's a lot more smooth to just plug it into a 3x3 matrix, calculate the determinant, and then the resulting vector is your cross product. So now that we know how to compute cross products using determinants in a much nicer fashion, let's talk about some applications. And so the first application I want to talk about is how to compute the area of a parallelogram. Computing the area of a parallelogram using the cross product. Okay, so let's say we have vectors v and u here. Notice if we took a copy of v, just like you do when you're trying to geometrically understand vector addition here, right? You take a copy of v and you place it at the end of u. And we also did the same thing with u. So here's like a copy of v. And let's take a copy of u, but place it at the end of v. Here's a copy of u. Notice this spans a parallelogram. The resulting shape is a parallelogram. And using, which means then, what are the side lengths here? Well, this side length has a magnitude of u because it's just however long the vector u is, right? And this side length has a magnitude of v because it's just however long the vector v is. And those are given by the magnitude. Okay, and so what's the area of a parallelogram? Well, the area is going to be the base times the height, right? And so we know what the base is. Well, the base is the magnitude of u. But what about the height? It's not quite v. It's not quite the magnitude of v, right? Because that's not the height of the parallelogram. The height of the parallelogram is going to be what's over here in green. But if we consider the interior angle theta, maybe I'll draw it over here. There's an interior angle between u and v, which we'll call theta. If that is the angle theta, well, then we know that the height here is the magnitude of v times sine theta, right? And so our height of this parallelogram is the magnitude of v times sine theta. But if you remember the theorem that we closed the video with, on the theorem that we closed the last video with, stated that this is exactly the magnitude of the cross product. So you can find the area of a parallelogram with adjacent edges u and v simply by calculating the magnitude of the cross product. This gives us a formula for calculating the area of a parallelogram just by knowing the vector representation of two of its sides, which is pretty cool. And we can take this a step farther and calculate the volume of a parallelepiped. Whoops, parallelepiped, right? So we can calculate the volume of a parallelepiped as follows. What's a parallelepiped? It's basically a three-dimensional it's the generalization of a rectangular prism in 3 dimensions, right? Just as like a parallelogram is the generalization of a rectangle in 2 dimensions. So a parallelepiped is, if you would like the analogy, is a 3-dimensional parallelogram. So if we have, let's say, vectors u, v, and some third vector w here, just as we traced out, here we kind of took the span, if you will. We took the span of the vectors u and v and traced out a parallelogram. Well, now we can take the span of u, v, and w, and we can get a 3-dimensional shape called a parallelepiped here. So its base, right? Like a slice, if you took a slice out, it would be a parallelogram, right? Just we're doing the same thing with u and v in 2-dimensional space, but now we extend that along the vector w. So we're going to take a copy of w at each vertex of the parallelogram, right? And then we kind of connect the dots here. And what we have is a 3-dimensional parallelepiped, which again, it would be like a slanted cube if you need to picture it. And so what is the volume of this thing, right? Well, the volume of this thing is going to be base times width times height. Okay. And so what is the height going to be, right? The height isn't W this time. So we know what the base, or let's not say base in this case, let's say length. It's a little more conventional. So the length is just going to be the magnitude of U, right? And we know that the width, which we were calling the height previously, is the width is the magnitude of V sine theta times whatever the height is, right? But we know that this is the magnitude of the cross product U cross V. And now we want to know, we need to take this times the height to get our volume, right? But what is the height? The height is not W. The height is represented by a vector that is purely perpendicular to both V and W, or both U and V, excuse me. This vector here represents the height. But how do we compute the height? Well, we can find a vector that's orthogonal to both U and V by the cross product, right? So the cross product will get us some vector that's perpendicular to both U and W. This is U cross V. However, it may not be exactly the height of the parallelepiped. How do we scale this cross product to the height of the parallelepiped? We take its projection onto the cross product. So the height is given by the projection of W onto the cross product U cross V. This gets us a vector that is perpendicular to both U and V, that is also the height of this parallelepiped, right? And so it's the magnitude here. And so this means that volume is magnitude of U cross V times the magnitude of the projection of W onto U cross V. And if you simplify this, I'm going to switch the order here. So if you simplify this, what is the magnitude of the projection? Well, last time we learned that it's the absolute value of, well, I'm going to slap on absolute value signs here because conventionally we want a positive volume, right? It's kind of odd to consider a negative volume. And so for that reason, I'm going to only consider the absolute value of the magnitude of the projection vector here. So this is the absolute value of U dot, or excuse me here. This should be W dot so this looks a little cleaner. Let's switch up our notation just a tad here. So this is going to be W dot U cross V over the magnitude of U cross V, right? Sorry. I confused myself with notation. I ended up not changing any notation right now. This formula here is simply what the magnitude of the projection is. And so this is all times the magnitude of U cross V, right? And so these cancel and we get W times U cross V. We get W dot U cross V, and we get its absolute value. Okay, and what this means is, let's recap. Volume of the parallelepiped with adjacent edges U, V, and W, whoops, is given by the triple scalar product So we have V equals, and now I'm going to kind of cycle the U's, V's, and W's. So it just goes in alphabetical order, right? And so this is, in general, the volume is given by the absolute value of U dot V cross W. Okay. And this is our formula for finding the volume of a parallelepiped. And so here, you know, you can see here, this was out of order. It goes WUV, and here I've gone, here I've gone UVW. I'm going to match the picture here. So my proof was kind of a permutation of what I'm calling the vectors. So to match here with this formula, we can think about the picture where this is the vector U up here, and then we have vector V and vector W. Okay. Again, it doesn't matter. Nothing's changed. I've just kind of flipped. I don't want to confuse you with my changing of variables here. But again, nothing's changed. And so now we can compute volumes of a handful of three-dimensional objects just by a few lines of vector algebra here. So lastly, to wrap this video up here, I want to talk just very briefly about a physics application. Physics application of the cross product is being able to compute torque. So let's remember what torque is. Torque, we'll denote it by the Greek letter tau, measures the tendency of a force to produce rotation about an axis of rotation. Okay, and so what do we mean, right? Torque measures the tendency of an object to move in a circular motion, right? Or that's what it means to move about an axis of rotation. A perfect example is tightening and loosening a bolt. If you have an extremely tight bolt and you want to loosen this bolt, the more force that's applied to loosen the bolt, the higher the torque of this wrench that's being moved in a circular motion. And for this reason, you know that the longer the wrench, the more force, the higher the tendency for this wrench to move in a circular motion, meaning the longer the wrench, the higher the torque. And so torque is a notion in physics and engineering and math, and it's everywhere, right? Just like work is, and we saw an application of the dot product for work. So let's look at a picture here. So let's imagine we have a bolt here. Okay, and let's imagine we have a socket around this bolt here. So I can maybe draw my socket in red. So socket kind of comes up like this, right? And then it's got a handle on it. Right, and then we would grab, can't draw a hand very well. We would grab the handle and we would try to loosen the bolt or tighten the bolt. So let's say we're applying a force in this direction, and force we can represent by a vector here. Well, from from the center of this bolt to where the force is being applied, you know, it's misleading because I would really like to consider it as the handle here. So let's just consider the center of our object at the top of the socket here, and the handle of the wrench here. This is our position vector, right? Well, which we'll denote by lowercase r. This position vector tells you like what's like your radius, right? This is moving in a circular motion. And so the position vector tells you like how far away are you from the center of the circle. It gives you the radius of this axis of rotation here. And now we are trying to calculate the torque, which is the tendency for the object to be moved when a force is applied. So we can kind of copy paste our force vector down here, and we have some angle theta that we're rotating here, right? And so this is kind of the picture you get. And torque can be calculated simply by taking the cross product of your position vector with your force vector. And you'll notice because of this, torque, the direction of torque is perpendicular. If you are trying to rotate something in the XY plane with a given force, torque is a vector that points perpendicular to the plane of motion. So torque, the resultant vector is up, because we've learned that the cross product gives you a vector perpendicular to both input vectors, right? And so here now, we kind of, I wanted to give a little visual picture, some intuition, and the formula for computing torque using a cross product. So we need to know how far away we are from a center or from this axis of rotation, and we need to know how much force we're applying at this distance. We represent these quantities as vectors, and we can immediately compute the torque just by taking the determinant of a 3x3 matrix, which is the same as computing a cross product. And so this wraps up our conversations on the dot products and the cross products. And we'll continue to use these through the rest of the semester, but this concludes kind of the introduction. Where we'd like to go from here is there's a little bit to be said on using vectors to describe shapes and surfaces and planes, et cetera, using vectors to describe all this stuff, and being able to take information encoded in vectors and translate it to information encoded in like algebraic formulas and stuff like this. So we can get lines, we can get equations for lines and planes and surfaces using vectors. And the cross product and the dot product are very relevant in this topic. After this, we'd like to shortly discuss vector valued functions, where, normally when you have a function, you input a number and the function crunches the number and spits out a new number. That's how functions work, right? They eat a number and they spit out another number. But vector valued functions behave differently. The input is a vector and the output is also a vector, which is why they're called vector valued functions. And so we'll get an introduction to vector calculus by looking at vector valued functions. And that will conclude our topics, or that will include our introduction to vectors and some of its applications. And then from here, we will kind of strap up and step to multivariable differentiation. So that's where we are headed from here.